So, we reviewed power series yesterday. We talked about the most important parts, which were finding a radius and interval of convergence, testing the endpoints. I think we multiplied a series out. Okay, so what we have left is really just a couple of things. We're going to do a division example, adding, which is going to be most important for us, is the adding. And then we're finally going to put it together for a differential equation. So let's look at this example here. Let's say we want to find the first four terms of the expansion for secant x. Well, secant x is what, really? Okay. And so, if we do some long division, you could do something like this. If we're just looking for the first four terms, we're going to take 1 and divide it by cosine x. So I'll just write out the first few terms for cosine x, which are 1, yep, minus x to the 6th over 6 factorial. We should probably actually figure these out. This is 4, that's 24, right? And 6 factorial is 5 is 120, so this is 720. Okay. And so we divide like normal just to get the first few terms. So if we're looking at this, 1 goes into 1 time, right? And now we're going to subtract the product, which is just going to be itself to start. Oh, no, it's just 2, which I wrote here, and for whatever reason, thank you, I wrote 2 over here. 2 factorial is 2. Okay, thank you. So then, write the few terms here. You get the idea. So when we subtract, 1 minus 1 cancels out, and now we're going to be left with basically the cosine expansion, but just we're switching all the signs. Does that make sense? So it'll be 1 cancels out, sorry. It'll be positive x squared over 2 minus x to the 4 over 24 plus x to the 6 over 720, and so on. And now we repeat the process. So 1 goes into this first term, exactly x squared over 2 times. Does that make sense? I know it's kind of goofy to think of it that way, but now we subtract. So now we're multiplying x squared over 2 to this. So that's going to turn into x squared over 2 minus x to the 4 over 4 plus x to the 6th over 48, and so on. Subtract. We really only need 4 terms. You guys see that, right? So that's why I'm not writing everything else out, because really I'm going to stop with these terms here. That's what I'm... What's that?
Why is it 4?
I didn't even hear, but thank you.
Yes, why is it over 4?
Oh, here? Yes, because you're multiplying the x squared over 2 to there. So the denominators are all going to get doubled. Okay. So subtract. Now the x squareds cancel out. And now we just have to figure out this fraction. So negative 1/24 plus 1/4 is going to be 5/24. And now we have 1/720 minus 1/48. That I can't really do in my head. Suppose you could just do it in the calculator. Yeah, what's that going to be? X to the 6th over something.
Yeah, 15x to the 6 over 48.
1/720 minus 1/48.
Negative 7 over 360.
Okay, I'll trust the calculator. And so on, but we don't need the other stuff because we're almost done. We just have to do this 2 more times. So what goes up here? Good. And now we multiply. Five x to the 4 over 24 times x squared over 2 becomes minus 5x to the 6th over 48, and so on. These cancel out. And now it's just, what is this going to be? Negative 7 3/60 plus 5/48.
Uh, 61 over 720.
Plus whatever, right? And we're done because 1 goes into this term exactly that many times, and that's all they wanted was just the first 4 terms. So these are the first 4 terms of secant x. Okay? So if you graph this, it should look something like secant x, at least to start. Okay? All right. Questions on that? So we did multiplying, we did dividing. Let's get to adding. So let's say we wanted to add these 2 series from n equals 1 to infinity. Let's say we have 2n times c sub n times x to the n minus 1 plus the series from n equals 0 to infinity of 6c sub n x to the n plus 1. Okay. So there's a couple of different ways that you can do this, but essentially what you're going to focus on to start is these. And more importantly, these exponents. Okay? Because what we're going to do is switch from n's to a new variable k. So here what we're going to do is let k equal this exponent, which is n minus 1, and here we'll let k equal n plus 1. And now we rewrite everything using the new variable. Okay? So if I do that, instead of n equals 1, now we start at k equals what? Exactly, because if n is 1, plug it in. Now we're starting at k equals 0. Does that make sense? And now you just got to go through every n and take care of it. So 2, instead of n, it's going to be, using this relationship, what's n? There we go. C sub k plus 1, and then x to the k. Plus, now we do the same with this one. If we're starting this one at 0, that means k is going to start at 1. 6 c sub, very good, k minus 1, x to the k. So that's the first move. Okay. Second, so first is this. Second, we want the start value to be the same. So we want to start at the same k value. This one starts at 1. We can easily make this one start at 1 by just plugging in 0 and figuring out what that looks like. Does that make sense? So plug 0 in. To get the first term. And then we should be okay. So if you plug 0 in, this becomes just the 2 and then C1. Does that make sense? And then x to the 0 is just 1. So plugging in 0 gives me just this 2C1 term. Now we finish, so we go the rest of the series from k equals 1 to infinity. And we still have 2k plus 1, c sub k plus 1, x to the k. And we still have this other one. Okay, but now that these indices match, if these match, we can now just put it into one series. And what we're going to get in the habit of doing, and you'll see that in a little bit, you see how both of these have x to the k in common, right? So what we're going to actually do is keep that out, like factor it out of everything, and just write down everything else that's left, which would be 2k plus 1, c sub k plus 1, plus 6 c sub k minus 1. So essentially we've grouped it. We have the first term from the first series right here. The second two series collapse into just this one. And these are the coefficients of x to the k, all grouped together. Okay? Probably should have written it in there first before I had to squeeze it in here. But that should say 6 c sub k minus 1. Okay? Does that make sense? Okay.
Doesn't k equal two different things? Like if you set them equal each other, don't you get 0 equals 2?
Set what equal to what?
N minus 1 and n plus 1.
Oh, you're talking back here? Well, they do.
It's like, how would you know which k to plug in if you use that?
Well, you're always, that's the whole point of switching the variables. So because we want, part of the thing that we want to do is make sure that these power, because remember, these are power series. If we have two separate power series being added together, we want to make sure that the power series start at the same exponent. And so that's why we switch variables here. Now what ends up happening, how we can just do that, well, this is why. This thing that comes out now allows all the other terms to be able to be combined into one series. Does that make sense? So that's kind of the process that you would take. And this will be important because when we start solving the, well, let's just get to it. Let's just do the example and it should come right up here. Okay. So we've done all the series review that you need to know. Okay. now it's time to see how we can use these to solve. So let's say we have the differential equation y double prime minus y equal to 0. And the goal here is to find a power series solution. Now keep in mind, you guys should be able to solve this without a power series actually really quickly. Okay, but just to illustrate how this works, okay, we're going to do it with the power series, and we should actually be able to check our answer sometimes, yeah, these will be a little trickier, but okay, let's just see what this turns into. So first what we're going to do, this is always the first step, okay, is we're going to let, since we're looking for a power series solution, we're going to let our solution equal a power series. So we're going to let y equal the power series from n equals 0 to infinity of c sub n x to the n. Okay, now typically if this is y, what did we do once we knew what y was? What did you do anytime you had like a particular solution or... If we're trying to solve this, and I'm telling you, we're going to plug it in, so that means we've got to take the derivatives, right? So let's take a look at what that looks like, and you're going to see that it's going to be the same thing every time, okay? So y prime is going to be, don't you get so excited, Crystal. Y prime is going to be the sum from n equals 0 to infinity. Take the derivative of a power like normal, right? So what's the derivative of this function going to be? There you go. Now we're going to go one term further. What happens if I plug 0 in for my first term? It's 0. So really, this is going to be the same as starting it at n equals 1. Does that make sense? Okay. Y double prime, so let's start over here, is going to be the sum from n equals 1 to infinity. And now the derivative of this power function, we have an n, and also the new power comes out, so that's n minus 1, c sub n, x to the n minus 2. But, same as before, if I start at 1 now, that first term is 0. So really we could just say that this is the sum from n equals 2 to infinity of n times n minus 1 times c sub n times x to the n minus 2. Okay? Does that make sense so far? All right. So, and you know what? I'm totally fine if you just remember this. These aren't going to change. Okay, and we're never going to ask, I don't think we're going to ask you to do anything higher than the third order, but if we did, you should be able to figure that out. Okay, so now let's plug these in. So now we're going to have y prime minus y is going to be, or I'm sorry, y double prime minus y. So we plug in this most recent one. Minus y, which was the sum from n equals 0 to infinity, c sub n x to the n. And now what we're going to do is kind of like what we did in the previous example. We're going to try to combine these. In fact, I'll let you guys have a minute or a few. So we're going to combine these kind of the same method that we used in the previous example. We're subtracting instead of adding, but it's the same idea. Okay, so see what you can come up with. Our goal is to eventually end up with something like this. Again, here are going to be my coefficients. You guys get one yet? What did we get for the coefficients?
K plus 2 times K plus 1 times C to K plus 2 minus or C sub K plus 2 minus C sub K all times X.
Good. Everybody good with that? Okay. So combine stuff. Here we don't, and well, that was a sum from K equals. Okay. So in this case, we don't need to plug in, and get like the first couple of coefficients. It just turns into this. And now remember, what does this equal originally? It equals 0, right? The original equation was equal to 0. So if that equals 0, okay, the only way that we're going to guarantee that this equals 0 is if all of these coefficients equal 0. Does that make sense? So next what we're going to do is take these coefficients and set that equal to 0. Okay? And when you get to this step, that's our third step now, is to find a relation, a recursive relationship between the coefficients. Okay, so this is two coefficients down the road compared to this one, right? So the best way to do this is to isolate the coefficient that's got the highest subscript. Does that make sense? So we can see how it relates to the previous ones. So if you isolate c sub k plus 2, you're going to get c sub k divided by k plus 2, k plus 1. And this is for, and you should specify, okay, we're starting at k equals 0, right? So this is k equals 0, 1, 2, and so on, okay? And so what we're going to do is use this relationship. So use this to find first several coefficients. Okay? So here's what's going to happen. And you guys know this already from experience. This is a second order equation, which means that we're allowed at most how many coefficients? How many constants are there if it's second order? 2, right? So C0 is going to be C0, C1 is going to be C1, and now here's where we start using our relationship, because when k equals 0, that's where we get C sub 2. Does that make sense? Okay, so using, where is it? Using this relationship right there, when k equals 0, plug that in. What do we get for that first coefficient? It'll be c sub 0 over 2 times 1, or just c0 over 2. Let's go to the third one. Plug in the third one. We get c sub 1 over, and these are just going to increase by 1 each time. You guys see that, right? So this will be 3 times 2, which is 6. Okay. And now c sub 4 is going to be c2 over 4 times 3. But remember, c2 is really c0 divided by 2. Does that make sense? So we're going to write that as c sub 0, and then keep the 4 and the 3 in there, but also throw in the 2. So we got 4 times 3 times 2 in the denominator. Okay? I'm going to go a few more. C5 will be C3 over 5 times 4. Once you get down a certain ways, you probably don't even need the formula so much, because you kind of know what's going to happen, right? What's C3? Well, C3 is C1 over 6, which was 3 times 2. I'm going to keep that in mind. So that'll be C1 over 5, 4, 3, 2. Yes. Do you guys see what's happening here? Okay, these are going to become 2 factorial, 3 factorial, 4 factorial, 5 factorial, right? I'm going to, again, just because it's the first example we're doing, we'll do 2 more. What's going to happen? I mean, you guys can predict it now. What's going to be the next coefficient? It goes C0, C1, C0, C1, right? So the next one is C0 over 6, 5, 4, 3, 2, 1, but we don't need the 1. And 7 would be the same. C1 over becomes 7 factorial. Okay. So let's see what this turns into. Well, we're pretty much done. The solving part now is just cleaning it all up and actually writing out our answer. Okay? So remember, And this is the first one we're doing, so this is why we're writing a lot down so that it's clear. Remember that our solution was y equals the sum from n equals 1 to infinity of c sub n, or I'm sorry, it was 0 to infinity of c sub n x to the n, right? So if you think about what that means c0 plus c1x plus c2x squared plus c3x to the third and so on, right? This is what our function is going to look like. Well, let's start writing it out. So c0 is good, c1 is good, but now here is where we start replacing, you see what I'm saying, with the coefficients that we got up above. So c2 is going to be c0 over 2, and that was going to end up being factorial, and that's x squared, plus c1 over 3 factorial, x to the third. Or I'm sorry, that wasn't 3 factorial. What was it? No, that was, yeah, x to the third, sorry, plus c0 over 4 factorial, x to the 4, and so on, okay? When the pattern is clear like this, you can just kind of do that dot, 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 right? And now what we're going to do is group our C0 terms together and our C1 terms together. So if I factor out C0, what we get is 1 plus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on, plus C1, and now here we'd have all the other terms, so that'd be x plus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. Okay? If we wanted to go one step further, we could actually write this in series format. This is just the sum from n equals 0 to infinity. And the rule here would be x, and then these are all just 0, 2, 4. So what's the exponent here? 2n. And the denominator would be 2n factorial, right? Plus c1, same thing over here. And now here we're just starting at the, let's do 2n plus, because if you do minus 1, then we're going to get the subscripts to not match. Okay, so then you'd have to change this. We always want to start it at 0 if possible. Which, by the way, and this is going to be a precursor to what we're going to talk about next, okay, does turn into something that we call the hyperbolic cosine function. You guys didn't do that in Calc BC, did you? So this is going to end up being nice for us to work with later on down the road. I'll kind of explain this at a later time, like what these definitions are, since we're almost out of time. But these, by the way, are just exponentials. It's like, what ends up happening is this. These eventually turn into some new constants. Let's call them C2, e to the x, plus another constant C3, e to the minus x, is what's going to end up happening. So all of these would be acceptable solutions. But if they want a series solution, you can just leave it like this. Even I don't care necessarily if you write it in its compact form, but as long as we see, these are the two solutions there, you guys are in good shape. Okay? Does that kind of make sense? Okay.